Alright, so today we're going to continue on with 10.4, but we're going to use what we learned in 10.4, the sum and difference formulas, to create or to prove the double angle identities. So we want to understand how to obtain the double angle identities from the sum and difference identities, as well as some uses to the double angle identities. So, obtain the double angle identity for sine given sine of 2x equals sine of x over x. So we'll go through this one together, and then I'll have you do the other two on your own. So, sine of 2x equals sine of x plus x. That makes sense. Well, what is sine of x plus x? Sine of x plus x is sine of x times the cosine of x plus the cosine of x times the sine of x. From here I can basically go to my answer because sine of x, cosine of x, and cosine of x, sine of x are the same thing. So this equals 2 sine of x cosine of x, which is my double angle identity for sine. With that said, I want you to show cosine of 2x, given cosine of 2x equals cosine of x plus x, obtain the cosine double angle identities. Pause the video, unpause when you're ready to check your work. Alright, this one should also hopefully be pretty straightforward and easy. Use your sum formula for cosine, so that becomes cosine of x times cosine of x minus sine of x times sine of x. Cosine of x times cosine of x is cosine squared of x. Sine of x times sine of x is sine squared of x. This is one version of my double angle identity for cosine. Remember, you have two other versions. You also have 2 cosine squared x minus 1, as well as 1 minus 2 sine squared x. Those can easily be obtained from your Pythagorean identities, substituting into cosine squared x minus sine squared x. Alright, maybe a little bit more work. Tangent of 2x equals tangent of x plus x. Pause the video and unpause when you're ready to check your work, but come up with the double angle identity for tangent. Okay, I was kidding when I said it was really actually more work. So all we have to do is plug this in the tangent sum formula, so I get tangent of x plus tangent of x over 1 minus tangent of x times tangent of x. The numerator becomes 2 tangent x, the denominator becomes 1 minus tangent squared x, and we're done. Alright, so now let's look at an example of an application. So I want you to solve sine of 2a times sine of a equals cosine of a. Notice that I'm just saying solve, so that means general solutions, not specific solutions between 0 and 2 pi. So I just want the general solutions. So I want you to pause the video and unpause when you're ready to check your work. Alright, so here the first thing I would recommend doing is bringing everything over to one side. Do not divide by sine of a, and recognize that sine of 2a times sine of a, that is not sine squared. Those are two different things because they have two different angles. So bring everything over to one side. Now convert sine of 2a into 2 sine of a times cosine of a. It still times this sine of a, so that still stays there. So now I have two terms, one here and then minus cosine of a. Both of them have a cosine of a in them, so factor out cosine of a. And then I'm left with 2 sine of a times sine of a, which gives me 2 sine squared of a, and then this becomes minus 1. Since this equals 0, I can set each factor equal to 0. So cosine of a equals 0, 2 sine squared of a minus 1 equals 0, gives me sine squared of a equals 1/2, which means sine of a equals plus or minus root 2 over 2. Where does cosine of a equal 0? Well, cosine equals 0 at pi halves and 3 pi halves between 0 and 2 pi. So as a general solution, that's going to be pi halves plus pi n. Sine of a equals root 2 over 2, positive and negative, at all of the pi fourth angles. All of the pi fourth angles conveniently are pi halves away from each other. So we're going to have a equals pi fourths plus pi halves n. So those are my two general solutions. Conclusion: understand how to develop and use the double angle identities. Good lesson.